Welcome to the 6.2 notes on piecewise-defined functions. The book spends a lot of time going into piecewise and step functions, and we're just going to do a little bit of an introduction on it. We're just going to do this one section for now on piecewise-defined functions and kind of apply it to what we did in 3.1 for absolute value functions. So if you haven't already done 6.1, make sure you do 6.1 before you do 6.2. Piecewise defined functions are defined for different rules for different intervals of the domain, okay? So we're going to be focusing on linear functions for our pieces, which will kind of make this a bit easier as we go through. So the structure is going to kind of look like this. I have f of x is equal to, but instead of having one function, I have two functions in this system. So these will likely be different functions. Well, they'll definitely be different functions. But they're going to exist for different intervals of x. So like x is greater than some number, and then this is going to exist when x is less than some number. So you're going to have a condition for some parts of x, and a different condition for other parts of x. I know this is probably looks really odd right now, but we'll go through piece by piece. I tend to use a comma here. I've also seen this written with an if on here. Okay. All right, so a quick reminder in case you're a little rusty on linear functions. F of x is equal to mx plus b, okay? Where m is the slope and b is the y-intercept. So for this first problem here, express the absolute value function given as a piecewise defined function. So I have an absolute value function, and I'm going to rewrite it as a piecewise function. I'm going to go ahead and I'm going to sketch this right here. I'm also going to show you how to do this in Desmos, but I'm going to do this first. All right. If I take this and I just do a really narrow sketch, remember that when I have f of x equals absolute value of x, that's the parent function, right? And I have a slope of 1 and negative 1. When I have a 2 in front, I'm going to have a slope of 2 and negative 2. So I get this graph here. Now going up to the right, this is a positive slope. So this has a slope of 2 on the right-hand side. If I point to it with my cursor. Right over here, this has a slope of positive 2, right? It's up to the right. If I were to write the linear equation of that, I could write y equals 2x. That only accounts for this piece, right? This is just piece of it. On the left-hand side, I could write y equals, this is a negative slope, so negative 2x. Right, I'm going to slow us down there before we write the function. I'm going to show you what this looks like in Desmos. All right. So I'm going to graph this function here. I'm going to graph f of x is equal to 2 times the absolute value of x. I'm going to check out that graph there. All right, there it is. So in case you're like, I don't know what that sketch looks like, you could get it right from here. We're going to come back to Desmos in a minute. I've got a vertex here at 0, 0. Okay. So I've got two different conditions here. I've got 2x and I've got negative 2x. Those are my two pieces of the linear equations. So 2x, when does this occur? I want to know the x values, always the x values, where this occurs. So what is the x value of the vertex? It's 0. So over here, this is where the positive numbers are for x. So this is going to be x is greater than 0. Well, in this case, I have y is equal to negative 2x when x is less than 0. So I've got two functions coming together, two linear functions coming together, and they change right here at this point where x is 0. Now, because this is a solid dot at the vertex, I need to pick which one of these is equal. Now, I've got a little note here on the right-hand side that says, you get to pick where the or equal sign goes in this instance. So it would be right for me to put it up here or for me to put it down below. I could put it either way. They would both be correct. So make a note of that. So it's also correct if you write the entire thing like this, but instead you have the or equals to on the bottom with the other function. That's fine too. Okay, so recapping what I did, I looked at the absolute value function. From that, I went, oh, this looks kind of like a line. What's the equation of this line? And I said, oh, this looks like a line too. What's the equation of this line? And I used those two pieces in my piecewise function. So where does the graph of f of x equals 2x exist? This occurs when x is greater than 0. Where does the line y equals negative 2x exist? This exists when x is less than 0. Now to graph that, well, let's do another one before I show you it in Desmos. Negative 3x, so the negative's going to flip it upside down. The 3 is going to make it narrow. Okay, and ask yourself on the left-hand side, what is the slope right here? Well, this is a slope of positive 3. This is the equation of the line, y equals or f of x equals 3x. The slope on this side is negative 3. This is the equation of the line, f of x equals negative 3x. So that's just identifying the equation of the line. You'll notice that if this is negative 3 times the absolute value of x, then this is 3x and negative 3x. You just have to pick which one's positive and which one's negative. Positive is up to the right. If it's helpful for you, a line that goes up to the right is always a positive slope. So I have 3x and I have negative 3x. This piecewise function changes from one function to the other at the vertex. That's where I change direction. What's the x value? I always want the x value when I'm talking about the condition. So let's see. Y equals or f of x equals 3x. So this one here. This occurs when x is, right, these are the negative numbers. Then we x is less than 0. Okay, on the right-hand side, that means that all of these ones, f of x equal to negative 6x occurs when x is greater than 0. One of these has to be or equal to, it doesn't matter which one you pick, put it somewhere. Now, piecewise functions can look a lot of different ways. This is just one way to describe an absolute value as a piecewise function. And we're going to broaden our horizons as we go through the notes. But I want to make a point that sometimes the book gives you a structure. Make that a little bit bigger. So let's say it gives you this structure. Have to fill it in, okay? So now I've got to be very purposeful. This says x is greater than or equal to, which means I'm basically going to write this one here. So greater than or equal to 0, that's fine. And then I know the negative 3x has to go here. X is less than 0. Which function goes here? 3x. So you may have to match them up and switch up the order that you write these in a little bit. Hopefully you can see how these are the same things. All right, so example 2, graph the piecewise-defined function. I'm sorry, before I do that, I'm going to go back and I want to graph this on Desmos for you. There's a condition that you have to use when I want to graph. I'm going to show you. When I want to graph piecewise, and you don't need this, so it may not register with you, and that's fine. I just wanted to show you. I'm going to use this kind of fancy bracket here, and I have to put my interval for x first. So I'm going to say x is greater than or equal to 0, and then a semicolon, given that x is, oh, which way did it go? Greater than was negative 3x. So that would be only part of my function, and then I would do it again. X is less than 0 for when the function is 3x. In Desmos, and I don't know why, Desmos has you write the interval and then the function. So check out how that's different. This is kind of nice too because you can see how they're different functions even though they look like the absolute value function. So check out how I wrote that down. You might want to jot it down or copy it into your Desmos screen so that you've got it. Okay. All right, so graphing the piecewise defined function. Oh, this moved a little bit. All right, now if I was in person, I would do this in pencil and then kind of erase it and redo it over in pen. So what I'm going to do here, I'm going to do a little bit of the same thing. You won't be able to see the pencil very good, but that's okay. I don't really want it to stand out. So I'm going to make it really light. Okay, so what I'm going to do here is I'm going to graph these two equations. So I'm going to graph y equals x plus 1. So that is a slope of 1 and a y-intercept of 1. Y-intercept of 1, slope of 1. This is hard to see on purpose. So if you're doing this on paper, I would suggest doing this part in pencil and then maybe doing the next part in pen or doing it something that you can erase with. So I graphed the entire function. Now this stopped at a certain point, but I'm just going to graph the whole line. This is f of x equals f of x equals x plus 1. And then I'm going to graph negative 3 halves x plus 6. So my slope is negative 3 halves, and my y-intercept is 6. 6, down 3 over 2, down 3 over 2. There's some way to have a ruler on this device. Whew, okay. So this is f of x equals negative 3 halves x plus 6. But they don't both exist in at the same time. So this change happens when x is less than 2 or x is greater than or equal to 2. So I'm going to kind of cut it off and highlight. So this first function that I did in this pink color, x plus 1, exists when x is less than 2. So x is less than 2, I'm going to go over and make this stand out. This is my answer. And this part over here I could erase or just leave it and just make sure it doesn't stand out. And then for negative 3 halves x plus 6, this exists when x is greater than or equal to 2. Right, so it includes that number. Okay. And then I can close like that. So that the pink and the purple part of those lines, that is my piecewise function. Now in example 1, my left-hand side and my right-hand side was a reflection. And example 2a, this is not a reflection. It's really close, I know. But I have a slope of 1 and a slope of negative 1.5. So they're not the same. The graphs also don't have to meet the same point. So we're going to do the same thing for B that we did for A. And these ones are actually not going to touch. They're not going to overlap at all. Okay, so I'm going to graph each one of them again. So f of x equals negative 3x. Slope is negative 3. Y-intercept is 0. Negative 3 over 1, if you will. Now that graph only exists when x is less than negative 2. So I'm going to go to negative 2. X is less than or equal to, so I'm going to have a solid dot here, less than or equal to. And the rest of it is really just my scratch work. It's not part of the answer. Then I've got f of x equals x plus 4. The slope is 1 over 1. The y-intercept is 4. This condition happens when x is greater than -2. So I'm going to go to where x is -2, go up, meet the graph, and then trace the part that I need. Now you may see something on here that you haven't seen in a while. I have an open circle. So why is this open circle here? The open circle is here because it's not included in x is greater than -2. It doesn't include that, right? It's not or equals to. So it starts at that point and moves forward, moves to the positive numbers in the positive direction, but it does not include that point. So you'll see here in example in B that these graphs don't have to meet. And I'm actually not even limited to 2 functions. I could have 4 pieces of a function on one. I could have infinite number of functions on one. We're not going to play with that today. But here's just 2 different linear functions on one graph as part of a piecewise function. All right. C, write a piecewise function for the graph. So now I'm given the graph and need to write the function. So a reminder, equations of the line are written y equals mx plus b or f of x equals mx plus b. So for this red line right here, I need to find the slope. I rise 1 and I run 3. So it's down 1 over 3. So I have a -1/3 slope. And then the y-intercept is -2. So I have -1/3 x minus 2. And when does that happen for x? So I could use a comma or I could use x. So x is greater than or equal to some number. So where does this graph stop? At 3. I look for the x value, so it stops at 3. And it's less than 3. It's all the numbers less than. So less than 3. And then is this going to be less than or less or equal to? Because it's solid, it's going to be less than or equal to. Okay. Next one. Now, this graph is distinctly harder to write because I can't tell what the y-intercept is. Right? I can get my slope up 1 over 1, up 1 over 1. So that's just 1x. But what's my y-intercept? I suggest you just use a ruler or your drawing feature to finish this line, keep going, okay, until you get an x-intercept. Then I can just write +1 here. That's the easiest way. So I've got f of x is equal to x plus 1. And when does that occur? Well, that happens at x is equal to 3. But it's going to be everything greater than 3, not including 3 because of the open circle. Now, if I wrote it this way and instead you had the whole top row on the bottom and the bottom row on the top, that is still correct. And awesome. All right, and lastly, for the piecewise linear function, find the f of -3, f of 0, f of 1, and f of 4. So this is what you're going to do as part of your steps. I'm going to ask myself, which interval does it lie in? Then I'm going to plug a number into x for that function. So I'll start with f of -3. And maybe I just identify these. Maybe I call this A, maybe I call this B if it's helpful. So f is, f of x is, x is -3, right? When I'm doing f of -3, I'm asking x is -3. So which condition does that apply to? The first one or the second one? Where can x be -3? Well, these are all the numbers less than or equal to 1. And these are the numbers greater than 1. -3 is less than or equal to 1. So that's going to be problem A. All right, so I plug it in to problem A. So I've got -3 minus 2, and I get -5. All right, so f of 0. When is 0, which interval does that fall in? A or B? So I look at the interval first, right? Here's the 0. 0, is it true that 0 is less than or equal to 1? Or is it true that 0 is greater than 1? No, it's true that 0 is less than or equal to 1. So I'm going to plug it into this function again. Oh, same function, okay. So f of 0 gets plugged into A, so that's going to be something minus 2. So I have 0 minus 2, which is -2. All right. So let's look at where 1 falls. Is 1 less than or equal to 1 or greater than 1? Well, 1 is equal to 1, so this falls under condition A again. So I plug in f of 1. I've got 3 of my 4 answers. One more. F of 4. Is 4 less than or equal to 1 or greater than 1? Oh, it's greater than 1. Finally. Finally meets this condition. So now I have to plug this into whatever the equation is that corresponds, right? So I plug it into here. So now I'm going to use -2x plus 3, -2 times x, which is 4, and then plus 3. I get -5. Okay, I hope that resonates well with you, sits well with you, yeah, and you understand this section a bit moving forward. Thank you very much for tuning in. Have a great day. Bye-bye.